All right, so what we're going to be looking at is the y values on the tangent line. So let me get a picture going here. So if I have a function, looks like this, and I've drawn the tangent line here, and you know a tangent line has to be talking about a specific x value. So there's your specific x value of a. So you can even see that the y values on the tangent line are close to the y values of the function. As long as you stay close to a, right? You can't be talking over here or way over here, but those y values are the same. So the y values on the blue tangent line we call L of x because they're on the line, right? So what we're going to do is we're going to start right there at this f of a, right? That's the y value that's on both the line and the function. And if I move over a distance of dx, right, gets me to this point. So this right here would be a plus dx. A plus dx. And if I want to find the y value on the tangent line that goes with it, I'm going to start with my f of a, and then I'm going to add on the dy. So you remember what the dy was? That was the distance change from the y value here to the place that it went up to on the tangent line. So f of a plus dy gets me to that y value on the tangent line, and that's what we're going to use as an approximation to the y value on the function. Remember, I've drawn this huge so that we get an idea of what's going on. Okay, so let's look at this one right here. So when it says use a linearization, that's the same thing as saying find the y value on the tangent line. So I need to create everything. I need to be creative mathematicians. So first off, I'm going to create the function f of x is equal to root x. So there's my function. And then I've got my nice number of 4, right? 4 here. And my dx will be 0.02. So here's 4.02. And I'm drawing a tangent line at the 4. Drawing tangent line there at the 4. Okay, so I go find dy, and you know the dy is f prime of x dx, so that's the derivative times dx. I calculate what dy is equal to. So put x equal 2 in, and put dx equal 0.02, so this gives me 0.05. So get another color in here. So 0.05 is the change in the y values from to this point here, the change in the y values that occur when I'm at 4.02. So it's that height distance right there. Okay, so what that means is the y value on the tangent line at 4.02, we're going to start at f of 4, and we're going to move up, because this turns out to be positive, by a distance of 0.005. So the y value on the tangent line at 4.02 is 2 plus 2.005, so this y value right here, if I had to find it, would be 2.005. All right, let's do it. And you don't have to have a picture. I'm just showing you a picture to try to give you understanding of what's going on. So let me do another one here. So you're going to be use differentials, or it's going to say use a linearization. Put that in parentheses. To approximate or estimate what this is. So first off, you have to create the function. So I see that the function looks like it's going to be x to the 1/3. Then I need to figure out what nice number for a I'm going to use. So I think that the value of x that I'm going to use, the specific a, is going to be 8. And then I'm going to use dx as 0.01. So let's go find dy. So you know dy is the derivative, right? So dy will equal 1/3 x to the negative 2/3 times dx. So doing a little bit of calculation here. Before I go do anything, I'm going to rewrite this as x to the 2/3 in the denominator. And so then dy will equal 1/3. And then I'll have 1 over 8 to the 2/3 times dx. And dx is 0.01. All right, so let's see what I got here. So you know that 8, cube root of 8 is 2, squared is 4, so I have 1/4, and then times a 0.01. So this total gives me 12, 1, 2, 3, 8, 3. and that's repeating. Okay, so now I'm going to fill in what I know here. So L of 8 plus 0.01 will give me f of 8 plus my dy. So f of 8 means put 8 into my original function, so that gives me 2, and plus my dy, that gives me 2.00083 as the answer.